Welcome everybody. In this tutorial we're going to talk a little bit about the applications of geometric sequences and series. So we already know quite a bit about geometric sequences and series, but just to recap in case we might have forgotten, a geometric sequence is one in which there's a specific relationship between successive terms. So for example, if we start with the number 2 and then we go to 6, then we go to 18 and then we go to 54. So there's a specific relationship between successive terms in that to go from 2 to 6 I multiply by 3, to go from 6 to 18 I multiply by 3, and to go from 18 to 54 I multiply by 3. So this is what we call a geometric sequence. It's one where the ratio between successive outputs is constant. That ratio we called OR. So OR is 3 in this case. And we also define the sequence in terms of its starting value, and we generally call that A. So our starting value for this sequence is A is equal to 2. We know that we can work out any term in this sequence given this information. So the nth term of the sequence is gotten by taking A and multiplying it by R to the power of n minus 1. And we can also sum up the first n terms of the sequence very easily using this formula, which we introduced in a previous tutorial. So the sum of the first n terms is given by taking a and multiplying it by 1 minus r to the power of n, all divided by 1 minus r. So once we know a and once we know r, we can do an awful lot of work with a geometric sequence. One of the areas where geometric sequences are very important and useful is in the area of finance, so when we're talking about savings and loans. So I'm going to show you how a geometric sequence can be used to help us deal with a savings problem. So let's look at such a problem. So let's suppose that I open a savings account. With €1,000 and deposit €1,000 at the start of the subsequent 2 years. If the account earns interest at an annual equivalent rate of 5%, how much is the account worth, or is in the account, at the end of the 3 years? Okay, so that's a fairly bog standard question that you meet in maths class when you're dealing with investments or savings. So you have all the tools necessary to be able to solve this problem. So you could do it as follows. We take the €1,000, and to work out how much that's worth at the end of the first year, we are going to multiply it by 1.05, and we're going to get €1,050. Okay, so that's the value of the account after the first year. Before we start the second year, remember we're adding in an extra €1,000. So that's going to give me €2,050 in the account at the start of the second year. So if we want to work out how much is in the account at the end of the second year, we're going to take that 2,050 and multiply it by 1.05 again. And when we do that, we're going to get an answer of €2,152.50. Okay. Again, we're going to add in €1,000 to this before the start of year 3. That's going to give us an amount equal to €3,152.50. And then to work out how much that grows to at the end of the third year, we're going to multiply that by 1.05 again. Okay, and that's going to give us an answer of €3,310.12.5. So that's the typical way that you will have done problems such as this and gotten your answer without very much difficulty at all. So this approach could be considered as a year-by-year approach. So we looked at the investment and how it behaved on a year-by-year basis. Now the problem with this approach is it's slow and tedious, so if we move beyond 3 years to 5 years or 10 years or even like 25 years, then this becomes far too laborious to do very much with. So what I'm going to do is I'm going to show you that there is an alternative way to approach this problem. So instead of looking at the problem on a year-by-year basis, we can actually think about it instead on a deposit-by-deposit basis. So what do I mean by that? Well, let's take the first €1,000 that is deposited into the account, and let's just look at that by itself for a minute. How much is that going to grow to by the end of the third year? Well, it's in for 3 years, so the value of that is going to be gotten by taking 1,000 and multiplying it by 1.05 to the power of 3, which is 1,157 and 62.5 cents. Okay, so that's just the first €1,000 we put in. Let's consider the second €1,000 that we deposit. So this one isn't going to be in the account for three years, it's only going to be in there for 2. So therefore its value at the end of the third year is just going to be gotten by 1,000 multiplied by 1.05 to the power of 2. Okay, remember we deposit that at the start of the second year, so therefore it is only in the account for 2 years earning interest. And when we work that out, that €1,000 is going to be worth €1,102.50 at the end of year 3. Let's take the third €1,000 I deposit. So how much is that going to be worth at the end of the third year? Well, it only goes in at the start of the third year, so it only earns interest for 1 year. So hence that's only going to be worth €1,050 at the end of the third year. So if I add up all of those, any guesses what my answer is going to be? Yep, you're right. So my answer is identical to the answer I got when thinking about this problem on a year-by-year basis. So instead of thinking about it on a year-by-year basis, we can think about it equally on a deposit-by-deposit basis. Now, why would we do that? That seems to be pretty much the same amount of work as doing it this way. Well, I'm going to show you now that we can cut down hugely on the amount of work we need to do just by examining the deposit-by-deposit approach a little bit more deeply. If we look at our deposit-by-deposit approach, you should notice something that is very interesting and definitely useful to us. So if we look at the successive terms in my deposit-by-deposit approach, to go from there to there, all I need to do is multiply by 1.05. To go from this term to this term, all I have to do is multiply by 1.05. So based on what we discussed at the start of this tutorial, what we should see very easily is that what we have here when we use a deposit-by-deposit approach is a geometric sequence. Okay, and the way that I'm looking at it, we can see that that sequence has a start value of 1000 times 1.05 to the power of 1. And it has a common ratio, so the ratio between successive terms of 1.05. So if I want to work out the total value of the savings account, all I need to do is add up the 3 terms in this geometric sequence. How do I do that? Well, I can use my formula. Sn is equal to a times 1 minus r to the power of n, all divided by 1 minus r. I want the sum of the first 3 terms, so S3 is equal to 1000 times 1.05 to the power of 1 times 1 minus 1.05 to the power of 3, all divided by 1 minus 1.05. And when I work that out, again, no prizes for guessing what my answer is going to be, I get €3,310 and 12.5 cents. So If I recognize continuous investments as being represented by geometric sequences, I can very quickly work out the total value of my deposits. So this approach becomes much more useful when we look at a more realistic real-world savings problem. So let's consider one. So suppose Jack opens a savings account by depositing €500. At the start of each year or each subsequent year, he deposits an additional €500. If Jack's savings earn interest at an annual equivalent rate of 3% and the account matures after 10 years, how much is in the account on maturity? Okay, so this is similar to the problem that we did a couple of minutes ago, the only difference being that we're dealing with 10 years. So if we did it on a year-by-year basis, we'd have to do out 10 separate calculations to get to my answer. But if I look at it on a deposit-by-deposit basis, so let's consider the first €500 that Jack deposits. How much is that going to be worth at the end of 10 years? Well, it's going to be worth €500 times 1.03 to the power of 10. Okay, I'm not going to work it out. I don't need to for what I'm going to do next. Let's consider the second €500. Okay, that's in for 1 year less, so that's only going to be worth that amount on maturity. Let's consider the third €500. So that's only going to be in for 8 years. Okay, because it's put in at the start of year 3. Let's consider the fourth €500. That's going to be worth this amount, and all the way down to the last €500 that Jack deposits, which is just going to be in the account for 1 year and hence is going to earn that amount of interest. So I could work out all of those individually and add them up, but that still is a little bit too work and too time consuming for my liking. But by writing out this sample of my deposits, what I should recognize is I'm again dealing with a geometric sequence, okay, one where the ratio between successive terms is 1.03. So to move from one term to the next, I multiply by 1.03. Okay, the same thing here, only we haven't written in the full sequence. And if I look as well, so that tells me that R is equal to 1.03. I can also see that first value in my sequence, if I look at it this way round, A is 500 times 1.03 to the power of 1, or just 500 times 1.03. Now, to find out the value of the savings account after 10 years, I'm going to have to add up all of these values. So again, I can just use my sum of a geometric sequence formula to do that. So the sum of the first 10 terms is gotten by taking A. So A is 500 times 1.03. All multiplied by 1 minus 1.03 to the power of 10 divided by 1 minus 1.03. And whatever value I get when I work that out is going to be the value of the account at the end of 10 years. So that wasn't very much work at all, considering it was a 10-year problem. So what you can see is that the knowledge that you have of geometric sequences is really useful, particularly here in the case of savings and investments. So one of the applications, one of the most popular applications of a geometric sequence is in modeling continuous investment problems.